Hey, thank you everyone for being here. I apologize for the delay. We had small technical difficulties, but we are now ready to start. We have the pleasure today of having David Spergel give our colloquium today. David got his PhD from Harvard in 1985. Shortly thereafter, he joined the Department of Astrophysical Sciences at Princeton University and has been a professor there since. He's now a professor emeritus at Princeton. In 2016, he became the founding director of the Center for Computational Astrophysics at the Flatiron Institute in New York. He's the co-chair of the International Astronomical Union Commission on International Cooperation and co-chair of the Nancy Grace Roman Telescope Science Working Group, which we will hear about today. He has received many awards and recognitions throughout his career, including the Shaw Prize in Astronomy in 2010, the Gruber Prize as part of WMAP in 2012, the Heinemann Prize in Astrophysics in 2015, the Breakthrough Prize in Fundamental Physics in 2018, and recently he's been elected honorary member of the National Society of Black Physics. So it's an absolute honor to have David tell us about his work today. So David, please, it's all yours.
So thank you for the introduction. I regret that we have to do this remote. This is the year we live in. I would very much like to, well, I wouldn't very much like to travel to Chile. I don't particularly enjoy the plane flight, but I would very much like to visit and I wish I had the opportunity to spend time there. But for now, we will have to get by with a remote tale. So what I want to talk to you about today is NASA's Nancy Grace Roman Space Telescope, a mission formerly called WFIRST, and sort of tell you a tale of dark energy and spy satellites. And as Cristobal mentioned, I am now at a fairly new institute. We're 4.5 years old, called the Flatiron Institute. It's a research-only institute focused on computational science funded by the Simons Foundation. And we're located in Manhattan, and hope that some of you will have the opportunity to visit us in 2021, which will hopefully be a more open and in many ways better year. So I'll begin with a picture of Nancy Grace Roman. Nancy Roman was the first director of astrophysics at NASA, a really major figure in building up space astronomy in the United States. She passed away a number of years ago, and the mission is named after her. I'll tell the tale of how we got to the mission. We ended up using a repurposed spy satellite, and that has all been part of the adventure. So what I'd like to do first is sort of step back. Not everyone is maybe familiar with where we are in cosmology. I will give you a very quick tutorial in cosmology, and then talk about how we got to this mission by describing the US Decadal survey process and the birth of the mission. Then talk about the telescope itself, its design, its science goals. Then talk about some of the science choices we'll be making over the next couple of years, and then conclude by describing the road to launch. So the overall picture I want you to have of our current understanding of cosmology is that we live in a simple but very strange universe. Over the past 20 years, cosmologists developed a very simple model, fits a host of astronomical data. Model rests on the idea that the laws of physics are valid throughout space and time, that the total energy of the universe is zero. The energy in expansion balances the energy in gravity, or equivalently, the geometry of the universe is flat. The surface area of a sphere goes as 4 pi r squared, regardless of the radius you look at. One of the interesting features of our current models of the universe, it seems that it underwent an early period of acceleration that generate a nearly scale invariant spectrum of fluctuations. And these fluctuations are what grew to form galaxies. So those pieces are all pretty simple, right? It's a fluctuation spectrum that's Gaussian, that's described by two numbers, an amplitude and how the amplitude varies with scale. Uh, that's about as simple as you can imagine for a fluctuation spectrum that would describe the properties of the whole universe. Its total energy is zero, the simplest possible geometry. The odd thing, or one of the odd things about our universe, is its composition. Atoms make up only 5% of the universe. The next roughly 25% is in the form of dark matter, and the rest is in the form of what we call dark energy, energy associated with empty space. So what the great mysteries of cosmology are include what is this dark matter, what's this dark energy, and what drove this early period of acceleration. So let's sort of step back and think about how we look out in space and back in time. As a cosmologist, I think of the starting point as the theory of special relativity. Light moves at a finite speed. Therefore, we see the sun as it was 8 minutes ago, Jupiter as it was a few hours ago, a nearby star as it was a few years ago, the Andromeda galaxy as it was roughly 1 million years ago. And the further out we go in space, the further back we go in time. When we go out and look at the microwave background, which I think you've heard about recently, some of the work we've been doing in Chile, for example, with the Atacama Cosmology Telescope, we're looking at the universe 13.8 billion years ago, so, which corresponds to roughly 300,000 years after. When we want to describe the universe on its largest scales, we rely on the idea that general relativity is valid on the largest scales. And when I talk about the evidence for dark energy, one of the things I'm assuming is that general relativity is working on those scales. And another intriguing possibility is that we're seeing the breakdown of general relativity, and that's something I'll say a few words about later on in the talk. As my academic great-grandfather, Johnny Wheeler, taught me, general relativity consists of two ideas. Matter tells space how to curve, and the curvature of space tells matter and radiation how to move. This was first tested back in 1919, over 100 years ago, with the great eclipse expeditions that measured the deflection of light by the sun as observed during the eclipse. And we've now tested it with increasing precision, particularly in recent years with results from LIGO, where we are able to test the predictions for black hole merger and see that general relativity is successful, certainly in the strong gravity limit. When we apply general relativity on the largest scales, we end up with the expanding universe, or so often called the Big Bang model, but I think of it as the expanding universe model. The picture I have is, I think about us living on the surface of a ball, where our galaxy is one of the galaxies painted on the ball. This is, of course, suppressing one dimension and treating the universe as if it had two spatial dimensions. The radius of the ball corresponds to time. So as the universe expands, it expands into the future. As the universe gets older, it gets bigger, bigger and bigger. The sphere continues to grow. As it grows, the microwave background cools. We can run that picture backwards. As the universe contracts, it gets denser and denser, hotter and hotter, until we get back to the moment where the whole universe collapses down at a point in time to a physical point. That expansion does not correspond, that moment of singularity does not correspond to a place in space, but a moment in time. That singularity happens everywhere in the standard Big Bang model. So now let's run things forward in time. We have as the universe expands, we believe it underwent an exponential period of growth called inflation during the first 10 to perhaps minus 32 seconds. About 100 seconds after the Big Bang, deuterium and helium formed. About a month after the Big Bang, we froze the microwave background spectrum. About 300,000 years, we look at the cosmic background radiation. When we look at distant galaxies and quasars, we're looking at roughly 100 million years after the Big Bang. Now, as I've mentioned, our observations of the microwave background in particular, together with our observations of large-scale structure, gave us a picture where the age of the universe is about 13.8 billion years, and it's composed of atoms, dark matter, and dark energy. This is a strange picture, and it's one, trying to understand this composition is one of the things that's driving a lot of the things we do in cosmology, this figuring out the nature of this dark energy. So that's all of cosmology and about a quick overview of cosmology in a bit under 10 minutes. So now I'll turn and talk about what's missing and how that drives the design of the next set of experiments. We're wondering whether general relativity has failed on large scales. Is there vacuum energy associated with empty space? Is space filled with a scalar field that's driving our expansion? So these were, a decade ago, what we viewed as our major open questions. Now, every decade, the astronomy community in the United States undergoes a process we call the Decadal Survey, where we get together and identify what are the most important science problems and what are the techniques we want to use to address them. It's something that I've been part of for the last 2 decades. Back in 2010, I chaired the panel on cosmology. It was one of the science panels. And our job was to identify the top science questions. As you'll see, that's what led to this mission. This decade, I am chairing the panel on what we're calling Enabling Foundations, which is a program committee looking at the projects we fund. And basically, we're responsible for identifying priorities for everything but the very large projects, very large projects like the next generation large optical telescopes and so on. So we get together, we have this process where we solicit from the broader US astronomy community, what are the big questions? We receive about 500 white papers, about 5 to 6 pages. We have this process first of science panels. As I mentioned, I led the cosmology panel in 2010, then prioritization panels looking at the projects we can lead. I've been leading one of the prioritization panels for the 2020 report. The 2020 report will be coming out early 21. Like so many things, it has been delayed by COVID, so it's a little behind schedule, but we've been moving forward with lots of Zoom meetings. My last trip in the before COVID days was to Washington, DC to chair the last meeting of my prioritization panel. We write these reports for many different customers, for government agencies, for Congress, for parts of the White House, the Office of Management Budget, and Office of Science Technology Policy. The one we'll write in 21, one of the things we're hoping it's for, or many of us are hoping it's for, is for a new administration that will, we will inform them on directions. We will find that out in November. Back in 2010, we identified 2 priorities as our top priorities. On the ground, the top priority was LSST, now the Rubin telescope. It's, of course, being built in Chile. It'll be getting first light, I think within about a year. Its focus is on studying dark energy, the variable universe, and has a broad range of applications in astrophysics. The top priority in space was not a mission that was proposed to the Decadal Survey. The Decadal Survey had 3 different proposals. One to study dark energy, another to study exoplanets through microlensing, another general astrophysics project to survey the universe in the infrared. The committee looked at these three proposals, all of which wanted a 1 to 2 meter infrared telescope in space, and suggested a dedicated mission that would be a survey mission that would do all three. So it midwifed the merger of these three science programs into one mission and named that the Wide Field Infrared Survey Telescope. Originally, the plan was for this to be a 1.6 meter infrared telescope. And that was what was proposed back in 2010. Unbeknownst to the Decadal Survey, the National Reconnaissance Organization, that's the organization that builds spy satellites that look down on the Earth and analyze things. They've actually built 15 telescopes that are the size of the Hubble Space Telescope, that instead of pointing up, point down and serve as effectively spy satellites. That the National Reconnaissance Organization had a canceled satellite program. They had built 2 satellites of what was supposed to be their next generation telescope. These were wide field mirrors, telescope systems operated, designed to do wide field imaging of the Earth. And these telescopes were sitting in Rochester, New York, because the program was canceled. They're basically sitting in storage. And they were thinking about destroying these telescopes because the program was canceled because it was over budget and they had been replaced by a new program. Fortunately, some of the people working at what is now Hughes Aerospace is they realized the potential value of this telescope, and the National Reconnaissance Organization approached NASA and offered it to NASA. Back in 2011, I was chairing the Committee on Astronomy and Astrophysics, which is the National Academy's committee that advises NASA on how to carry out the Decadal Survey. I was approached by the then head of science at NASA and was told, we just got this 2.4 meter size telescope. That's bigger than the telescope that the Decadal Survey wanted. Do you think this bigger telescope would be useful for carrying out the WFIRST mission? And this was an exciting thing to be able to consider with this more powerful telescope that now has the resolution of Hubble and basically twice the collecting area. We would be able to carry out an even more ambitious program from space than was envisioned in the Decadal Survey. And one of the things that we recognize, and this is something that I worked closely with my colleague Jeremy Kasdan on, who's done a lot of work in coronography, is that we could not only carry out the program of studying dark energy, exoplanets, and general astrophysics, but we could add a coronagraph and use this as a stepping stone for the program of imaging Earth-like planets around other stars. So that's how the current form of WFIRST was born. And that a few months ago was renamed Roman after Nancy Grace Roman. And here is what the mission basically looks like. It now consists of 2 pieces: a wide field instrument doing imaging and spectroscopy over thousands of square degrees. The imaging instrument has 18 H4RGs, makes a 288 megapixel camera. That's 100 times the field of view of Hubble and JWST. So as I'll return to at the end of my talk, the image to have of what comes out of this telescope is you take every picture Hubble has ever made, now make it 100 times bigger. And you gain more than 100-fold because of operations overheads or less in your ability to survey the sky. So realistically, we can survey in the lifetime of this mission the entire sky at Hubble resolution. Right now, Hubble's covered less than 1% of the sky in its long lifetime. In addition to the wide field instrument, there's a coronagraph that will image and take spectra of exoplanets. Will not have the sensitivity to image and characterize Earth-like planets, but we'll look at things from the super-Earth to giant scale, image to Greek drifts, and develop the technology needed to be able to image Earth-like planets. So in its new form, this mission has 4 pillars. General astrophysics has 100 times the field of view of Hubble. So you can sort of take the Hubble program and now do things that are much more ambitious. For example, you can survey the Andromeda galaxy, not in 400 pointings, but roughly 2 pointings. It will play, and this will be the focus of a part of my talk, a role in studying the dark universe by making precision measurements of the expansion of the universe and a large-scale distribution of dark matter. It'll also give us insight into the population of exoplanets. It should detect thousands of planets and through microlensing, characterize the occurrence rate of these systems. In doing so, it will nicely complement the Kepler and TESS missions. Those are sensitive, as the figure in the lower left corner shows. In red, Kepler and TESS are sensitive to planets whose semi-major axis is less than an AU. They were effectively planets that are closer to their host star than the Earth is to the sun. WFIRST, on the other hand, through microlensing, is sensitive to more distant planets and will characterize the properties of Mars and Jupiter and Saturn and Uranus and Neptune-like planets in these systems and really complete the census of the properties of extrasolar planets, terra systems. It'll also be able to directly image planets and with so take large steps towards imaging Earth-like planets around nearby stars. So one way I like to think about this, I had the pleasure of being at the 2019 Nobel Prize ceremonies I got to see my colleague Jim Peebles from Princeton win the Nobel Prize for his work in cosmology. Here's a picture from his talk. And in his talk, he listed the big questions in cosmology. What is dark matter? What is dark energy? How did the structures we see evolve to make the galaxies we see? How did the universe begin and what is its fate? And these are the questions we'll be studying with the Roman Space Telescope in cosmology. I also got to hear the exoplanet talks for the shared part of the prize. And here's Didier Toulouse talking about what he sees as the open questions in exoplanets. What explains the diversity of planetary systems? What are the properties of exoplanets? Do they host life? And again, these are the questions that we will be focusing on with the WFIRST mission, the Roman mission. This again gives you a sense of the camera compared to the imaging capabilities of Hubble and James Webb. You're covering far more area with this camera. With that, you can now address a pretty wide range of questions in dark energy. We can study the dark energy properties in a number of different ways. The way I think about this is we have sort of 2 broad handles on probing the effects of dark energy. One is to measure distance versus redshift. It was through measurements of distance versus redshift with supernovae, work largely done in Chile, that we were able to first see the evidence of cosmic acceleration. And now that, that will be a technique we will extend further by using infrared observations from space, extend that to nearly redshifts of 2. We will also measure distances to galaxies using as a ruler the baryon acoustic oscillations that we see both in the microwave background and the large-scale distribution of galaxies, probing them with H alpha emissions from redshift 1 to 2, and through galaxy oxygen 3 emission from redshift 2 to 3. And finally, we will use weak lensing, both as a way to probe distance and to measure the growth of structure. We will complement these growth measurements through measurements of cluster growth and looking at redshift clustering. Now, this combination of testing gravity, both by looking at the relationship between distance and redshift, which probes the homogeneous part of general relativity, the overall growth of the universe, and looking at how structure evolves, how the universe gets more and more clustered with time, which probes the growth of the sort of the perturbation part of general relativity, lets us test whether what we interpret as cosmic acceleration is really due to energy associated with empty space, or whether it's due to dark energy. If we see a consistent answer with both methods, that points to a success for general relativity and an evidence for dark energy. On the other hand, if we see different answers as we look at structure growth and distance measurements, that potentially points to a failure of general relativity on the largest scales. And to me, this possibility of answering these questions are, for me, the most exciting part of this mission. It's a very broad science program, so different people get excited about different parts, but this is where the study of dark energy, where my heart is. We will be able to, when you work in the infrared, and this compares infrared and optical images of distant galaxies, we really gain a lot in the ability to do lensing work. It's going to be much more sensitive and higher resolution than other dark energy instruments. European Euclid mission will launch in 2022. It'll be a big advance, but Roman should be the step beyond that. Either Euclid will see hints of something interesting that we will be able to test and confirm, or it may require the sensitivities ultimately that we will get, as I'll mention at the end, by really combining the Roman Space Telescope and the Rubin telescope to achieve the most powerful results on probing the large-scale distribution of dark energy. And this sort of shows how dense the galaxies will be in the Roman survey compared to the Euclid one. Let me keep moving. I've mentioned the synergies between these missions. This shows how sensitive they are across the sky. What's shown here is the depth in green of the Euclid survey, the depth in blue after 10 years of operations of the Rubin large-scale survey, synoptic survey of the sky, and in red with WFIRST. This is assuming we use WFIRST to only cover 2,000 square degrees. An alternative I'll talk about is to simply use the widest band in WFIRST that covers Y, J, and covers J, H, and F 148 bands. So it extends almost from 1 to 2 microns, the widest band. That widest band would let us survey the entire sky with the same level of sensitivity as LSST. Euclid is actually very well matched to the LSST first year data. So I anticipate what we'll be doing in the early 2020s is combining the LSST data with Euclid to survey the sky at sort of a depth of 24th magnitude. And as we look towards 10 years of data, we'll be combining LSST data and WFIRST data, surveying the sky roughly 3 magnitudes fainter, a factor of more than 10 gain in sensitivity. So let me now turn to how we plan to use the telescope. I meant this, I always tell my students never to show tables of numbers. Here's a table of numbers, which I'll leave recorded for people who want to know the sensitivities of the telescope. this shows the basic parameters in the bottom for the planned LSST survey in terms of sensitivity and what bands are covered. And in the top, the planned sensitivity for our baseline survey for WFIRST, for the Roman telescope. Now, what I should stress with this is what we've done at this point is we've put together what we call a design reference mission. It's a use case, how we might use the telescope in its first 5 years. We look at what our science goals are. We look at possible strategies for observation and put together an observing program. This design reference mission lets the engineers design first the hardware and then the software needed to get the data down, analyze it, and operate the telescope. But it does not represent the mission that we will actually likely carry out. We will likely do something quite different from the design reference mission. And one of the things that NASA will be doing over the next couple years is carrying out a series of competitions and a process to have the broad astronomical community drive the choices in how the telescope is used. And what I want to describe in the remainder of the talk is actually some different possibilities on how we might use the telescope. For example, just focusing on this high latitude survey for dark energy, one possibility, and this is the baseline sort of shown here in terms of sensitivities and the bands here, is we survey the sky in 4 distinct infrared bands covering about 2,000 square degrees in our imaging survey and roughly the same area in the spectroscopic survey. Another possibility, and one that I'm excited about, and one that we recently published a paper outlining, is one in which we say, let's take advantage of the fact that we now know we're carrying out the Rubin survey, that we shouldn't rely on the space survey to get multicolored data over the whole area. Let's use the widest band in the Roman telescope in WFIRST, and get to the depth of LSST across the entire LSST footprint. So we would then have Hubble quality imaging on every galaxy that LSST is using in its sample. What we've showed in this paper is just for dark energy applications alone, there'd be an enormous gain. That if we define a figure of merit of how well we characterize dark energy using something that's been sort of a standard metric in dark energy studies, that by carrying out this wider survey, we would outperform LSST and WFIRST high latitude survey by factor 5, and the year 10 LSST survey by factor 2.5. And this would only require 5 months of observations with WFIRST to survey the entire footprint. And we would provide a legacy of really Hubble quality imaging that will be useful for many things. So this is what I'm actually quite excited about right now, is this possibility of Roman-Rubin synergies. And here is a picture in the red of Vera Rubin, one of the pioneers in the study of dark matter, and Nancy Grace Roman, one of the pioneers in building up space astrophysics. This is at a meeting, I believe, held in Maryland a number of years ago, but before their recent deaths. And just as this meeting brought the two of them together, I would like to see us bring together the data, both these data sets. This would give us really high quality photoses. This would also give us, for galactic astronomy, for example, very accurate astrometry for all the LSST data. We should achieve milliarc second and likely sub-milliarc second astrometry by tying to the Gaia reference frame for all this data. We will produce useful science on topics ranging from brown dwarfs, stars, very low mass stars, very massive stars, the active galactic nuclei. Uh, it'll be an enormous amount of science that we can get out of by devoting only 14 weeks of telescope time to these observations. So this is something I hope we will do. I also hope we will use the telescope and not only go very wide, but go very deep. One of the more dramatic pieces of science from the Hubble telescope was the Hubble ultra deep fields, where the telescope stared at one part of the sky for a month. With the Hubble telescope, with this much larger field of view, staring at one part of the sky, we can survey 1/4 of a square degree, uh, detect hundreds of millions of galaxies in this deep image. And for me, most excitingly, we can get at very distant galaxies in the very early universe, look very far back in time. If our current models are correct, we will see over 10,000 galaxies at redshifts beyond 8, thousands beyond redshift of 10, hundreds beyond redshift of 12, and even tens beyond redshift of 15. This ultra deep field would be a wonderful training ground for identifying targets for the next generation large optical telescopes, including, of course, the big ground-based telescopes are going to be built in Chile and the James Webb Space Telescope. So I think these possibilities of using this telescope both to go very wide, study dark energy, very deep to study the most distant galaxies will have enormous impact on our understanding of cosmology. So all sounds great. How do we build this multi-billion-dollar mission? Well, it's a long journey to build something of this scale. This project started in some ways back in the late 1990s. Saul Perlmutter proposed a SNAP mission, a mission to study cosmic acceleration. Saul would go on to win the Nobel Prize in 2006. About the same time, a number of us were proposing to build a smaller telescope to survey the whole sky in the infrared. Back in the late 2000s, around 2007, 8, NASA and the Department of Energy pursued what they called the Joint Dark Energy Mission, a series of studies, 3 competing projects to study dark energy. Because of the difficulties of working together between 2 agencies, as someone at NASA told me, it's so much easier to work with the European Space Agency or work with the Japanese, those people in the Department of Energy. That project fell apart. As I mentioned, the Decadal Survey then revived this possibility in 2010 by proposing the WFIRST mission, which then led to the first studies of a smaller mission. The National Reconnaissance Organization Optical Telescope Assembly became available, publicly known in 2012. We then organized in 2013 a meeting to talk about the science you can do with this, help put together a case to convince NASA to start studying a science definition team. We put together, I think, a compelling case, which led to a study in 2014. While there was enthusiasm within NASA, the budget people in the Office of Managing Budget, the people who actually implement the recommendations that come from the White House on budget, were opposed to NASA starting any new large telescope until James Webb was finished. They zeroed the project multiple times. We have the honor of being zeroed by both the Obama administration once and the Trump administration 3 times. So I spent had many trips on the train to go to Washington, and we were able to convince Congress to restore funding every cycle. We have now gotten to the stage where we have spent 1.2 billion, actually now this year probably close to 1.5 billion. The mission has passed what NASA calls key developments point C, which is the point at which you actually start building all the hardware, and the mission is considered approved for launch. So it is now being built. It was zeroed one last time in this year's budget. Again, strong congressional support saved the mission, and we're now on track for a 2025 launch. So let me end the politics by going back to the science, or at least leave you with an image in the end of what we will be able to do. We are building a telescope that will have 100 times the field of view of the Hubble telescope and the same resolution. With this tool, I think we will have the ability to have potentially transformative discoveries, the nature of dark energy, the evolution of galaxies in the early universe, the properties of exoplanets, and a wide range of problems in astrophysics. So let me conclude there, take questions, and thank you for listening. Bye.
Thank you, David. Thank you for this wonderful talk on this wonderful telescope. Any questions from the audience?
I have a question. Can you hear me well?
Yep, just perfect.
Okay. Well, thank you
Yes.
for the talk and the presentation of the telescope. I wanted to ask you, in your opinion, or based on the expected performances, can you comment on the complementarity or main differences between the Euclid mission and the WFIRST mission for addressing dark energy related questions, the nature of dark energy?
So Euclid will survey the sky. Let me go back to these sensitivity plots. It will survey the sky in the optical, in a very wide band, and in the infrared, survey at about 24th magnitude. So it will be sort of most sensitive to the evolution of the universe between today, looking back to about redshift of 1. And if the interesting properties of dark energy are revealed over that redshift range, then Euclid, and actually spectroscopically, also the ongoing DESI survey, will likely be the ones that make the first kind of breakthrough discovery. And then Roman and Rubin will play the roles of confirming and getting more precise versions of those measurements. On the other hand, if the key insights or the discovery that awaits us is mostly between redshift 1 and 2, then I think Roman will turn out to be the most powerful telescope for studying that. So in a sense, they're quite complementary. Euclid should launch first, so we will get those results first. And in fact, we will be able to modify the Roman observing plan to be most complementary to the results from Euclid. I'm actually part of the US Euclid science team, as well as being active in the Roman telescope. I think it'll be terrific to have these multiple tools. I think in some ways this may parallel what we did in the microwave background with WMAP and Planck, where WMAP first made precision measurements across the whole sky of the fluctuations, and then Planck was able to, a decade later, with higher sensitivity, to get improved measurements. So this time the agencies are switched, but I think it's very useful to look in multiple different ways. I mean,
Thank you very much.
Yeah.
Andreas, Radwan, are you gonna um, ask something?
Yeah, I have maybe
ahead.
just it's well. Thank also for the very nice talk. I wanted just to ask something about. It's more like vocabulary, actually, more than a deep question on cosmology. Is that you have quoted the words of Wheeler about space-time tells matter how to move and matter tells space-time how to curve. And I think we should keep that philosophy about the fact that general relativity does not tell us at all about what kind of matter.
Yeah.
That's whatever matter we put, then we get some reaction. And but it doesn't tell us if there is dark matter or if this is a quintessence field, a scalar field, or vacuum energy, etc. So if we discover that finally it's not a cosmological constant, but for example, a quintessence field, it's not a failure of general relativity. It's just we discover what is the content of the universe. So I wanted to know if you agree on that, not to say that this is a test of general relativity, but more about a test on the content of the universe.
So this is something, ooh, will this work? Okay, let me see if you can see I'm gonna try to write equations on my board. And hopefully this will be legible. So what I think of as the basic equation of cosmology is the Friedmann equation that relates the expansion, the Hubble constant. Expansion rate to the density. And as you said, we can take any measurement we have of the Hubble constant, and that just tells us how the density evolves. So, there's I'm basically measuring H of Z with these distance measurements, and that gives me rho. And that tells me whether it's dark energy, dark matter, vacuum energy, all that. I can then look at the evolution of density fluctuations. And if general relativity is the right theory of gravity, then density fluctuations evolve under this perturbation equation, which I think goes back to Lifshitz, that says delta dot plus 2h delta, should have my iPad hooked up, is equal to 4 pi g rho delta. Now, once I've measured H of Z, that completely specifies the evolution. So no matter what the dark energy is, once I know H of Z, that tells me how density fluctuations evolve. Now, what happens if I measure the evolution of density fluctuations and it doesn't follow this equation? That would be a failure of general relativity. So if I take an alternative theory of gravity and look at the perturbation equation, it looks different. And in fact, what you see is the density fluctuations evolve differently with redshift. You can measure the rate of growth of fluctuations and measure the slope. And because you know H of Z, there's a very exact prediction that general relativity makes. And many of the alternative, we don't really have a great alternative general relativity. I don't think there's anything that's really that attractive, but the ones that people have written down do lead to different predictions. And in terms of measurement, I think of this as we both want to measure distance, which is this part, and the growth of density fluctuations, which is this part. And we should get consistent results from that, assuming general relativity is correct.
Okay, thank you.
Yeah, I mean, my own bet is general relativity is the success, which has been so successful, will continue to be successful, that we're learning about dark energy. But I think it's important to always be trying to test your assumptions. And so that's why I try to frame it that way.
Thank you. So Andreas Reisenegger was asks on YouTube, are there any plans for powerful ultraviolet telescope?
Yes, by the Chinese. So the Chinese are building their own space telescope that will fly off the Chinese space station. Also launched in the 2020s. It's called the CSST. It will have a CCD camera. Remember, this is an infrared camera. The CCD will go into the ultraviolet. It will do visible bands in a way that I think, to me, the visible capabilities of that telescope are less exciting than the ultraviolet ones. So we could actually add to this plot some points over here at about this sensitivity, further to the ultraviolet than accessible from ground, and actually more sensitive than LSST will be in the ultraviolet band, which is, the atmosphere limits the Rubin telescope in the ultraviolet and in the infrared. So we'll have better performance from space, from the Roman telescope, and from the Chinese telescope in the blue. Putting on my hat for the IAU, one of the things that I hope we can achieve in the 2020s is a sharing of data so that eventually everyone in the world will have access to, when it becomes public, the Rubin data, which I think becomes public after a couple years, the Roman data, which becomes public immediately, and the data from the Chinese Space Telescope. To step into geopolitics for a moment, there's been a lot of tension at times between the United States and China. And I think that science, and particularly this kind of astronomical surveys, offers an opportunity for cooperation. So that's a long-winded answer to, that's how I think we'll get ultraviolet data.
Thank you. And Andreas says thanks as well. So let me ask you, as a theorist, do you think theory will keep the pace as the observations come along, or we will be theory starved at some point with all these data?
Well, I would answer that in two different ways. There's a piece of theory, right? If we want to understand the nature of dark energy, nature of dark matter, the physics of inflation, that all requires physics beyond the standard model. And our ideas there have been driven by ideas that have come out of particle physics, areas like supersymmetry, developments in areas like string theory. I'm, hopeful that our particle physics colleagues will continue to come up with new ideas. I think when I talk with them, I try to get them to feel that, which I think is true, that it is astrophysics that is actually offering them the most important evidence for physics beyond the standard model. And that while a lot of them have been waiting for new insights from the LHC, it may be figuring out, they need to come and help solve our problems. So there's that piece of theory. There's another piece of theory where, and this, I think, is whether you call this theory or data analysis or given these big surveys and these enormous amounts of data, how do we analyze this data? What techniques do we use? And this is a place where I think machine learning can be incredibly powerful. In the past 5-6 years, there's been tremendous advances in machine learning. And their sort of classic problems are things like classifying faces or reading numbers on a piece of paper. So they do image analysis. well, as astronomers, we have lots of image data. And I think there's a potential, well, I'm confident that machine learning will be useful. It will be a tool that we'll use that will help us in our data analysis. The most exciting possibility is that it is transformative, that we can use it in a number of different ways to find new insights from the observations. And the thing that I'm excited about as a theorist, sort of wearing my relatively new hat as a director of a computational institute, is that it will provide a way of letting us derive subgrid physics from numerical simulations. When we look at these problems in cosmology, they have enormous range of scale. We will never be able to fully simulate everything from the scale of the universe to the scale at which star formation takes place. Yet all those scales interact. And a whole nother talk is the possibilities of using machine learning to do multi-scale physics, which is one of the things I'm very excited about.
Mm-hmm. Thank you. Do you have any other questions? What about the astrophysics? You mentioned the very high redshift galaxies that you will see with the Roman telescope, that we will see with the Roman telescope. What about not the most distant galaxy, the faintest galaxy, but any galaxy at say redshift of a half, or any sort of not discovery space in that sense?
Yes, I think there what you will be gaining is infrared data on those galaxies, right? So you've got optical data, well, some already from Hubble, but right now you can get data on redshift 1 galaxies in the infrared from Hubble, but it covers a very small portion of the sky. So what you will gain here is the ability to really survey large areas of the sky in the infrared. The infrared is more sensitive to the integrated starlight, to the more massive, to the lower mass stars. So you're getting sort of integrated star formation histories that complements the observations you get in the optical, which represent rest frame ultraviolet. So most of the light you're seeing in the optical from galaxies at redshift of a half is coming from the youngest stars. So that's tracing what's happening now with star formation. And this will complement it by giving you integrated integrated information. There, I think it's thinking about what you've been able to do, say, by combining data from Subaru and LSST and Hubble, and now imagining doing that over a much larger area. The other area of general astrophysics that I'm excited about is actually astrometry with WFIRST. So Gaia has put out some wonderful results in the past several years, giving us precision measurements on the positions of stars down to 20th magnitude. Because WFIRST will be in such a stable environment, it will be out near orbiting the second Lagrange point in the Earth-Sun system. It should be actually a terrific telescope for astrometry. And because we can use Gaia to tie down the reference frames, we think we should be able to achieve better sensitivities than Gaia does on stars dimmer than about 18th magnitude, and have, Gaia will have milliarcs, has arc-second astrometry on 20th magnitude stars. WFIRST, a Roman, should have milliarc-second astrometry on 25th magnitude stars. So you can push much further out in our galaxy in studying main sequence stars, looking at things like tidal streams and things like that sort. So I think that will be very interesting for galactic astronomy. For studying the nearby universe, we will be able to image basically all the nearby galaxies at Hubble sensitivity. So one of the major programs with Hubble over the past decade has been the FAT survey led by Julianne Del Canton, that has imaged Andromeda with Hubble. What we would like to do is with Roman is image, we can do that program more than 100 times faster. So instead of just doing Andromeda, you can survey all the nearby galaxies, and with that learn a lot about their star formation histories and their assembly history. So I see that as among the areas of general astrophysics that will have a big impact.
Mm-hmm. Thank you. And Andreas has another question. What is your bet for the nature of dark matter and dark energy?
My bet for dark energy is vacuum energy. It looks so close to what it's behaving like. And my bet for the theory of vacuum energy is a bit of almost a Kabbalistic numerology. There are two scales I know about in physics. There's the Planck scale and the scale of electroweak symmetry. If we have some mechanism like supersymmetry that cancels the vacuum energy down to the supersymmetry scale, the next scale would be something that goes as m supersymmetry squared over m Planck. That number turns out to be just the right number to explain vacuum energy. So I don't know how to do that calculation, but that's what I would guess is the answer for vacuum energy. For dark matter, for a long time, I thought the most likely possibility was associated with the WIMP miracle, the idea that supersymmetry was near the weak scale and that it would explain both the hierarchy problem and the existence of dark matter at the same time seemed very attractive. However, the failure of the LHC to find evidence for supersymmetry, I think, makes it interesting to think about a much wider range of possibilities for what dark matter could be. So I think it could be anything from a really light axion-like particle, all the way up to some Planck scale particle that we haven't seen evidence for yet. So I think it's the possibilities for dark matter are really wide open right now.
Okay, that seems like a great place to end then. Thank you very much again, David, for giving this talk. Thank you everyone for listening and making questions. As you know, the talk will remain available in our YouTube channel, so you can check it out whenever you like. Thank you, David, and have a good rest of your day, and everyone.
Great, thank you, and thank you for inviting me to talk, and hope to see you all in person in the not too distant future. Thanks.
Yes. Goodbye, everyone.
Bye.
So